Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So today we are going to discuss about the module Electro-optical and Magneto-optical Effect from the paper Electronics. So students, let us see what we are going to learn in this module. First, detailed explanation of anisotropy and permittivity tensor will be discussed. Second, the theoretical description of electro-optic effect will be discussed in this module. Third, we will also discuss about the magneto-optic effect. So students, let us start with a basic introduction about the module. The invention of optical fiber has led to many applications in the modulation and transport of monochromatic light for transmitting information to long distances. Fiber optic systems find numerous applications in computer networking, scientific measurements, defense sector, etc. Optical modulator is an integral component of fiber optic communication system which can modulate the laser light beam, that is frequency, intensity, phase, polarization in accordance with the externally applied electric field. So optical modulation performing the operation of external modulation are advantageous as compared to the direct modulation. So electro-optic EO modulators utilizes the EO effect exhibited by anisotropic material, where there is a change in the refractive index with the applied electric field. A large number of EO modulators uses Pockel's EO effect, where variation in the refractive index of crystal is linearly proportional to the magnitude of applied electric field. So the optical properties of a material can be modified by applied electric or magnetic field. So the change in the refractive index as a function of applied electric and magnetic field is responsible for many electro-optic and magneto-optic effects. They can be regarded as non-linear optical mixing effects in the limit where one of the field components is of zero or nearly zero frequency. Optical anisotropy. Birefringence is a property usually associated with transparent crystals with a non-centrosymmetric lattice structure, for example calcite. The electric vector of incident plane polarized light entering a birefringent medium is split into two mutually perpendicular components called as the ordinary and extraordinary rays. The electric field of the O ray is always perpendicular to the optic axis, so its refractive index N0 is a constant independent of propagation direction. The index ellipsoid equation describing the optical anisotropy of a crystal can be written as x square by nx square plus y square by ny square plus z square by nz square equal to 1, where nx, ny and nz are the principal refractive indices along the respective axis as shown in this figure. So this figure shows the refractive indices associated with the two plane waves propagating along the arbitrary directions k in a crystal. In the case of biaxial system, there are two optical axes and the refractive indices are different in all the three principal directions, that is nx not equal to ny not equal to nz. The birefringence of the medium n theta depends upon the propagation direction and is defined as ne minus n naught. The maximum birefringence occurs when theta is 90 degree, that is when the electric field of the E ray is parallel to the optic axis, and it is given by n equal to ne minus n naught, where ne is equal to ne at theta equal to 90 degree, and n is defined as the difference between the refractive indices of the O ray and E rays of fully oriented nematic phase, propagating parallel and orthogonal respectively to the optic axis of the nematic medium. So birefringence is responsible for the appearance of interference colors in LCDs operating with plane polarized light. Interference between the extraordinary ray and ordinary ray, which have traveled through the medium with different velocities, give rise to the colored appearance of these thin films. Students, let us discuss about the permittivity tensor. The modulation of the properties of light propagating in an optically anisotropic crystal is the fundamental principle for the development of electro-optic device. Permittivity of the material can be characterized by its optical and dielectric properties, and it is an important parameter for the description of EO effect, and therefore its origin can be explained. That is, polarization is an important phenomena while studying the EO effect, where relocation of both the bound free charges in response to the electric field within the material takes place. So, in an isotropic medium, the induced polarization P and the electric field E, they are related by a scalar field factor chi called as susceptibility, and the relation is given by P equal to epsilon naught chi E, where epsilon naught stands for the permittivity of vacuum in an anisotropic material. The induced polarization depends on the direction of the electric field vector, and it becomes necessary to define the susceptibility as a second rank tensor. So each of the polarization component Pi is dependent on all the three components of the electric field Ej, and can be written as by the Einstein notation Pi equal to epsilon naught chi ij Ej, where I and j can be 1, 2, 3. So here the permittivity tensor relates the electric field vector and the electric displacement vector d as di equal to epsilon ij Ej, and thus defines the dielectric properties of the crystal. If the medium is homogeneous, non-absorbing and magnetically isotropic, the permittivity tensor can be shown to be symmetric using the principle of the conservation of EM field energy. So the same analysis applied to a non-absorbing optically active medium shows more general result, that is, epsilon ij is equal to epsilon ij star, where epsilon ij is the complex conjugate of the permittivity epsilon ij star. So the symmetrical property of the permittivity tensor makes it possible to find a coordinate system in which the tensor has only its diagonal elements. The axes of such a coordinate system are called the principal dielectric coordinate axis and are of great importance for the description of the electro-optic effect. So students, let us now discuss the theory of electro-optic effect. In the presence of an applied DC or low frequency field, that is E naught, we have the optical dielectric constant, that is epsilon omega comma E naught, is a function of E naught. So for small sufficient value of E naught, epsilon omega E naught can be expanded into power series of E naught as epsilon omega E naught equal to epsilon 1 omega plus epsilon 2 omega plus omega E naught plus epsilon 3 omega plus 2 ohm E naught square plus so on. So since E plus 4 pi p equal to epsilon E, and if the dispersion of the medium is neglected, then the polarization P will be equal to chi 1 omega E plus chi 2 omega plus ohm E naught plus so on, where chi represents the susceptibilities defined only in terms of Fourier components of field and polarizations. Now here omega is associated with an EM wave E and ohm equal to 0 be associated with a static field E naught. So the incident field contains two frequencies, that is omega and ohm. Now E plus 4 pi p equal to E plus 4 pi chi 1 omega E plus 4 pi chi 2 omega plus ohm E naught plus 4 pi chi 3 omega plus 2 ohm E naught square E equal to epsilon 1 omega E plus epsilon 2 omega plus ohm E naught plus epsilon 3 omega plus ohm E naught square E. Now this is obtained by putting equation 9 and 11 in 10. Thus epsilon 2 omega plus ohm equal to chi 2 omega plus ohm, and epsilon 3 omega plus 2 ohm will be equal to chi 3 omega plus 2 ohm. In a non-centrosymmetric medium, that is, no inversion symmetry, electro-optic effect is dominated by epsilon 2 term, which is linear in E naught. So the epsilon 2 or chi 2 tensor produces polarization components P2 omega, which is proportional to E naught E. These polarization components vary linearly with E naught, and this is termed as Focal's effect. However, in any material with or without inversion symmetry, the quadratic field dependent term always exists, and it is known as Kerr effect or quadratic electro-optic effect. The epsilon 3 and chi 3 tensor produces polarization components P3 omega, which is proportional to E naught square E. So the quadratic EO effect is much smaller than linear EO effect. For isotropic material, quadratic EO is the first non-zero non-linear optical effect and is low. So the electro-optic coefficient Rijk can be related as 1 by epsilon ij E naught equal to 1 by chi square ij E naught equal to 1 by chi square ij 0 plus summation over k Rijk EOK plus k summation over kl Pijkl EOK EOL, where Rijk and Pijkl are linear and quadratic electro-optic coefficient. So delta 1 by eta square will be equal to summation over k Rijk EOK plus summation over kl Pijkl EOK EOL. So the field induced refractive index give rise to linear birefringence, and for a birefringence crystal, eta naught is not equal to eta E. Thus, because of different propagation velocities, when light propagate in birefringent crystal, the two modes have different phase delays, and the phase difference is given by phi OE equal to 2 pi by lambda d multiplied by eta naught minus eta E, where d is the crystal length. So with applied zeta, eta naught and eta E changes, implying phi OE changes, which leads to delta phi OE. So the variation in phase retardation induced by zeta causes manipulation of the polarization state of light beam. Physically, electro-optic effect results from both ionic and molecular movement and distortion of electronic cloud induced by applied zeta. Even if induced, delta eta is proportional to 10 to the power minus 5. So typical values of Rijk is approximately 10 to the power minus 10 to 10 to the power minus 8. A medium 1 centimeter long can impose a phase retardation greater than pi by 2 on the beam of visible light. This is the reason why EO effects have been widely used as optical modulators or optical switches. Some devices can be used as optical modulators or switch depending on the strength of interaction between optical waves and controlling signal, as well as on the arrangement of the input and output ports. So the crystals of lithium niobate, lithium tantalate, gallium phosphide, zinc oxide have large linear EO effect for certain orientation. So we can write it down that a modulator, its primary function is to impress the information on a light wave by temporarily varying one of its properties, and switch changes the spatial position of light or turning it off and on. Basic characteristics of switches and modulators. Modulation index or modulation depth eta. In the case of intensity modulator, where applied zeta acts to varying intensity of light, is given by eta equal to eta naught minus I divided by I naught, where I naught is the value of the intensity of light when zeta equal to 0, and it is transmitted intensity with applied zeta. This is denoted by I. However, when intensity increases with zeta, then eta will be equal to I minus I naught divided by Im, where Im is the transmitted intensity when zeta equal to zeta max. Similarly, for frequency modulator, eta is f naught minus f divided by f naught, where f naught is the optical carrier frequency and f shifted optical frequency. Bandwidth represents the range of modulation frequencies over which the device can be operated is defined as delta F equal to F upper minus F lower. F upper and F lower, where modulation depth falls to 50% of its maximum value. Switching speed or switching time t is given by t equal to 2 pi by delta F. Now let us discuss about a single waveguide EO modulator. Waveguide may be planar or a channel guide. It can either be a phase modulator, an amplitude intensity modulator, or a switch as shown in this figure. So the total change in refractive index between guide and substrate is delta into 3 equal to delta in chemical plus delta in CCR plus delta in EO, where delta in chemical is the refractive index change due to different aluminium concentration. Delta in CCR is the change in index due to decrease in carrier concentration in guide, and delta in EO is the index change due to electro-optic effect. So for the waveguiding of a given mode to occur, the condition is delta n equal to n2 minus n3 greater than ma square lambda naught square divided by 16 n2 minus n3 tg square, where ma equal to 2m plus 1 is the mode with m equal to 0, 1, 2, 3, so on. Tg is the thickness of waveguide. The confinement will be poor for small n and or large lambda naught by Tg. For asymmetric waveguide, N2 is approximately N3, then delta N equal to N2 minus N3 greater than Ma square lambda naught square divided by 32 into Tg square. For phase modulator, the dimensions and the doping of waveguide are such that it is above the cutoff frequency for m equal to 0 mode at desired, but it is below cutoff for m equal to 1 mode. Thus, we can say lambda naught square divided by 3.2 eta 2 I naught square is less than delta eta chemical plus delta eta CCR is less than 9 lambda naught divided by 32 omega 2 multiplied by I naught square. When reverse bias V is applied to the Schottky diode, waveguide becomes a part of depletion region. Zeta causes the change in the phase of light wave traveling along the guide that is proportional to V. So the change in the refractive index, that is delta eta EO, will be equal to N2 cube eta Rijk V by 2 I naught, where however delta eta equal to delta I by K equal, this is delta beta. So delta beta is the change in the propagation constant along z-axis. This implies that the change induced by zeta is delta phi EO equal to delta beta multiplied by L equal to pi n2 cube Rijk VL by lambda naught I naught, where L is the length of modulator in Z direction. So intensity modulation delta N at waveguide substrate interface must be tailored to make the waveguide be just at threshold for guiding the lowest order mode without zeta. When zeta is applied, there occurs change in refractive index which causes the waveguide to become transmissive. Thus, zero field threshold condition for an intensity modulator is delta eta to 3 will be equal to delta eta chemical plus delta eta CCR, and hence it becomes equal to delta eta chemical plus delta eta CCR plus delta eta EO when zeta is applied. Magneto-optical effect. Michael Faraday studied the magneto-optical phenomena, that is the effect of magnetic field on properties of light propagating in a medium placed in a magnetic field. So magneto-optic rotation is an effect that relies on rotation of a polarization plane of linearly polarized light during its propagation through a medium placed in a magnetic field. If a magnetic field H0 is applied along the propagation light direction, such phenomena is called as Faraday effect, and if the field is perpendicular, it is called as void in gases or cotton mountain in liquid. So this figure shows the polarization plane of linearly polarized light which rotates upon propagation in a medium in H0. Optical dielectric tensor epsilon of the medium is also a function of DC magnetic field H0, which has a symmetry relation as epsilon ij H0 equal to epsilon ij minus H0. In a non-dissipative medium, it is Hermitian. That is, epsilon ij H0 equal to epsilon ij prime H0 plus j epsilon ij double prime H0 equal to epsilon ji star H0. This implies epsilon ij prime H0 equal to epsilon ji prime H0 equal to epsilon ij prime minus H0. That is, real part is symmetric and even function of H0. Imaginary part is antisymmetric and odd in H0. So this implies epsilon double prime ij H0 equal to epsilon double prime ji H0 equal to epsilon double prime ij minus H0. So dependence of epsilon double prime ij on H0 leads to circular birefringence on the Faraday effect, while dependence of epsilon ij prime on H0 leads to linear birefringence or cotton mountain effect. Hence, different refractive index is induced by H0, resulting in different velocity for different components of light in medium. Faraday observed that for a light propagating through a medium, the angle of magneto-optic rotation phi is phi equal to VL H0, where H0 is the applied magnetic field strength, L is the length of active rotating medium, V is proportionally constant known as Werde constant. So analogous to EO effect, MO effects can also be used for optical modulation. The Faraday effect or circular birefringence causes linear polarization of a light beam traversing the medium to rotate. In low field limit, phi is proportional to H0. The effect is much weaker in cotton mountain effect, proportional to the square of field intensity H prime, and applied perpendicular to the propagation of light direction and has limited applications. So students, let us summarize what we have learnt in this module. First, the detailed explanation of anisotropy and permittivity tensor was discussed. Second, theoretical description of EO effect, including the description about the basic characteristics of switches and modulators, was discussed. Third, single waveguide EO modulator was discussed in this module. Lastly, we also discussed about the magneto-optic effect. Thank you.